In this video, we're going to introduce the concept of a sampling distribution. This is super important because we are going to be using sampling distributions for the remainder of this course. Sampling distributions are what connect us from normal distributions and random variables to being able to make inferences about a population based on sample data. They are what bridge the gap between samples and statements about the population, and that's the real power of statistics. A sampling distribution is a distribution of sampling statistics. We can build sampling distributions for any statistic, but the two most common that we're going to see are for sample means and sample proportions. If you read chapter 7 in your text, you'll also notice that they look at sample sums, but that isn't something that comes up very often, and we're not going to cover it in this course. We're going to start by focusing on sample means. So a sampling distribution is constructed by collecting samples of size n from a population, specifically all of the possible samples of that size from a population, calculating those sample means, and then plotting them on a graph. There are two important properties of these sampling distributions. The first is that we expect the mean of a sampling distribution should be equal to the mean of the raw data from that population. Because those samples are coming from the population, we expect that those samples should be clustered about the population center. And so the center of the sampling distribution, the center of those sample means, should be the same as the center of the raw data itself. You'll notice a new notation, the mean of the sampling distribution for sample means. So we're labeling sampling distribution variables with a subscript that indicates they're from a distribution of sample statistics. Right now we're focused on sample means, so we're looking at a distribution of X bars. The other important fact or property of these sampling distributions is that the standard deviation of the sampling distribution is smaller than the standard deviation of the population. So if I collect a sample of heights from students at Shasta College, I expect that sample is going to have some tall people and some short people. When I find the average of that sample, those extreme short and talls get squished in towards the middle. And if I repeatedly collect samples, I'm squishing all of those extreme values in towards the middle. I expect the sample means should be a lot closer to the actual mean than the individual data values, which could be extremely low or extremely small. So looking at sample means instead of raw data takes those extreme values and squishes them in towards the middle, which reduces the spread of data, resulting in a smaller standard deviation. Specifically, for a sampling distribution of sample means, the sampling distribution standard deviation, which is also sometimes called the standard error, if my pen would work. So you'll sometimes see standard error instead of standard deviation, and if you see standard error, you know you're talking about a sampling distribution instead of a list of raw data. So the standard error for the mean is equal to the standard deviation of the population divided by the square root of the sample size. What that means is that as my samples get bigger, my standard error will get smaller. As my samples get smaller, my standard deviation will get bigger. Because smaller samples, you get less of that squishing towards the middle process. There are fewer data values to cancel out those extreme values, and so the spread of the data is going to be more in a sampling distribution based on small samples than on a sampling distribution based on big samples, where we get more of that averaging process that squishes extreme values in. You don't have to remember the fine details. What you do have to remember is that this is going to change a couple of calculations. First, when you use inverse normal and you're looking at a sampling distribution, your mean doesn't change, but your standard deviation does. And that's the last value you plug into normal CDF. That's going to shift. That also changes how we calculate z-scores. So if you're asked to calculate a z-score and you're working with a sampling distribution, your z-score formula is going to look different. It's going to be, instead of a raw data point, it's now a sample mean minus the population sampling distribution mean divided by the standard error, or the standard deviation of the sampling distribution. It's still data value minus population value over population standard deviation, but now those values are coming from a sampling distribution instead of a list of raw data. This right here is the formula you would actually use, because we know that the mean of the sampling distribution is just the mean of the raw data. The standard deviation is the standard deviation of the raw data divided by square root of the sample size. So if you are asked for z-scores, modified formula. That's less common because our calculators can calculate probability even if I haven't converted all of my data to z-scores. I don't have to work with the standard normal distribution. For probability questions, as mentioned before, that last data value that normal CDF is going to ask for becomes sigma over square root of n instead of sigma. So if you are working with a list of raw data, so raw x values, you're using just the regular sigma for the population data. If you are working with samples of size n, meaning you're working with a sampling distribution, you need to use sigma over square root of n in those function calls. We have 2 more videos coming that are going to go over how to do these types of problems. If you have any questions about what you just saw, feel free to send me an email or drop by office hours. Otherwise, I will see you in the next video.